ह्याच्यातलं ना. हॅलो. 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 कॅन यू हिअर? नो. हॅलो. 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 माइक टेस्ट. हॅलो. हॅलो. माइक टेस्ट. हॅलो. 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 माइक टेस्ट. माइक टेस्ट.
Good afternoon and welcome to all of you to this special lecture which is held in memory of Professor Bimla Buti. She was an eminent woman scientist and a role model to many of us who passed away recently in February. This lecture is supported by Buti Foundation and Veena Ramani, present president of Buti Foundation, could not be present here today physically as she is abroad. So she has sent a message in few slides and I'll first like to read that on behalf of her. So this is a message from Veena ji. At the outset, let me congratulate the organizers of the Vigyan Vidushi 2024 physics program for their successful endeavor in bringing together young, bright minds of our gender studying physics in colleges in the year preceding of their acquiring the postgraduate degree. From the length and breadth of our nation, exposing them to advanced research topics and opportunities in physics through lectures and mentoring sessions. This should go a long way in motivating them to pursue research careers in physics and increase in the number of women physicists. It would help to mitigate the gender bias that one sees in our society. So a bit about Professor Bimla Buti. She says that she is the founder president of Buti Foundation, a role model for many young women scientists. Vinaji further goes on, it was a big loss to me and my family when Dr. Bimla Buti left us after a sudden and brief illness 3 months ago in Ahmedabad. After a very successful research career in physics and after great many contributions to the society through many world physics forums, she was carrying out a number of philanthropic activities under the banner of Buti Foundation during the last few decades. During the last phase of her life, she left the activities to be continued on my shoulder. Her trust and confidence in me are driving force behind all the present foundation activities. Bimla Buti pursued studies and research in very difficult conditions. She was born in Lahore, erstwhile Integral India. She had her early education there. During partition, she moved to Delhi, where she had her higher education. Her father's unstinted support enabled her to pursue research. She went to Chicago, completed her PhD, and returned to India with the entire family giving her a great reception at the airport. I would like to add here that she did her PhD under the guidance of Professor S. Chandrasekhar. PRL Ahmedabad was her main workplace. So Dr. Buti worked in many organizations, Delhi University, IIT Delhi, NASA, but her mainstay was Physical Research Laboratory Ahmedabad. She guided 5 students for PhD and collaborated with innumerable number of colleagues. Known for her strict discipline in her way of work, she imparted that profusely to all around her. She was one of the most distinguished physicists in the country and was globally acknowledged for her fundamental contributions to understanding of chaos. Internationally known as an authority on nonlinear dynamics, her work found applications in widely varying plasma systems, including astrophysical plasma. In this picture, you see her father and brother from Delhi grace the occasion when she won prestigious Vikram Award at PRL. This is her picture with Professor Chandrasekhar when he visited Ahmedabad in the 80s. Here you see Dr. Buti in different roles. She served as a director of ICTP, Plasma Physics School, for many years. She was known for taking meticulous care of Indian students in Trieste in Italy. And you see some of the pictures here. Post-retirement from PRL, Dr. Buti instituted the Buti Foundation and initiated a number of awards through scientific institutions and societies. She founded the Center for Science and Society with branches in Delhi, Bareilly, Indore, and Ahmedabad. She got immersed in philanthropic activities. So we'll see some glimpses of that. This is for the Center of Science and Society at Ahmedabad. This is the Buti Digital Education Center at Ahmedabad. And this is Mahatma Gandhi Allied Health Science Institute at Indore. Bareilly Cancer Trust, which is where she adds that Buti Foundation continues to contribute regularly towards free medicines and running free medical camps at Bareilly Cancer Trust, an activity which Dr. Buti initiated many years ago. Free computer coaching is also provided for deprived children through the Center for Science and Society, Bareilly. Almost all Dr. Butti's interviews emphasize the need for promotion of women in science. Two of Professor Butti's interviews, which were telecast and are available on YouTube, have been published in two books by Vigyan Prasad, Scientifically Yours, Selected Indian Women Scientists, and Moments of Eureka, Life and Work of Selected Indian Scientists. To inspire young girls to choose science as a career, Department of Science and Technology, through an NGO Sparrow, published a book, The Balancing Act, Stories of Women in Science. Butti's story appears in this book. Lilavati's Daughters, The Women Scientists of India, published by Indian Academy of Sciences. Celebrating Achievements of Indian Women Scientists, book released by Department of Biotechnology, Government of India on International Women's Day, March 2019, also features her stories. I'm sure many of you will see some of these things. So Dr. Buti appears in The Chosen Few Indian Women in Science. This is the book we talked about. And now Veeraji mentions about Buti Foundation's support to Vigyan Vidushi program. As a person who worked extensively for the promotion of women in science, Vigyan Vidushi Physics program is such an activity that comes very close to her heart and mind. Hence, the Buti Foundation naturally comes forward to support the noble deeds of this VV 2024 physics program to its best possible extent. Buti Foundation assures its continued support to this program in future years too. Thank you, Veeraji, for your kind support and kind words. I will take a moment here to add my personal memories of Professor Bimla Buti. I was privileged to have known her and interacted with her. In the first edition of Vigyan Vidushi in 2020, we had a lecture by Professor Bimla Buti, which is available on the YouTube, as I told. And one interesting episode I want to add here, that in 2021 March, the TIFR archives put up a special board on the International Women's Day about women in TIFR. And while doing so, they actually found a job application by Bimla Buti for TIFR. And this, she had forgotten about it. So she had written to then director Professor Menon, and who actually told her that there is a new institute getting set up in Ahmedabad, which has a plasma group, and you apply there. So she, I think, went initially to Delhi IIT and then moved to Ahmedabad eventually, which became her main workhorse. So one of the things which, as I have said, that is a mantra which she, whenever I interacted with her, and even when she talked to our Vidushi students, is what she told was, don't give up. And that was something which she actually very strongly believed in. Her story is very, very inspirational. And we are indeed very happy to have Professor Rupamanjari Ghosh today to give this first Bimla Buti Memorial Lecture. Professor Rupamanjari is also an example of amongst very few women achievers who have kind of, break the glass ceiling and rise to the top. She served as a Vice-Chancellor of Shiv Nadar University, Delhi-NCR for 2 terms till January 22. She was the founding director of the School of Natural Science and the founding dean, Graduate Studies and Research at SNU. The SNU became an institute of eminence within a few years of its existence under her leadership. She is a former professor of physics and dean of School of Physical Sciences at Jawaharlal Nehru University, New Delhi, where also she has started many initiatives to improve the gender equity. She has a very well-recognized PhD from the University of Rochester, New York, USA, where she worked as a Rush Rees Fellow, chosen for outstanding scholarly ability and the promise of exceptional contributions to scholarship and teaching. Besides her contribution to science research and training from university to school level, she is also well known for her stand and efforts to bring in gender justice, environment consciousness, and sustainability in the higher education system. So we couldn't have found a better speaker. And today she's going to talk about quantum century. And I think there's an additional sort of a good coincidence is that we are expecting that today the United Nations will make a formal announcement about 2025 being declared as International Year of Quantum Science and Technology. So with these words, I now welcome Professor Rupamanjari for a lecture.
So, good afternoon. Thanks, Vandana, for that nice introduction. And I'm really honored and privileged to deliver this first Buti Memorial lecture. I have a habit of walking up and down, but I'll try to stick to the map.
Okay, now we are.
Yeah, fine.
Just
Thanks. So there are many special things about this lecture this afternoon. First is the Vigyan Vidushi program. You guys are all very special. It's a special program being run by somebody very special, Vandana Nanal, and I'm really privileged to be hosted by her. When she first time wrote, and I know I did a bit of running around. I took the morning flight to arrive here, and I'm going to take a flight back in the evening because there are many things happening in Delhi. But I'm just so glad that I could still make it. There are some tense moments. So first began Vidushi, second Vandana Nanal, and I don't have to say it, you already saw that this is the first memorial lecture, first one on Professor Buti. So okay, I first go there. Sort of lost the control. This it's not coming. There. It's thinking a bit too much. So up. No, thanks. Does it work? Let's see. Should work, right? Okay. So this definitely is dedicated to Professor Bimla Buti. I've interacted with her only a couple of times, but those have left very permanent impressions in my mind. So without wasting any more time on the delicacies, as Vandana asked me that, first 8 to 10 minutes, I'll probably talk a bit about the journey I had and the lessons that I have learned along the way. So I'm just going to give you a summary, no anecdotes, and all of that has to wait for some other lecture. So I hope all of you know that when everybody is talking about the UN Sustainable Development, there's so many goals, 17 that are there. Goal number 5 is very special, and I want each one of you to know that. Goal 5 talks about achieving gender equality and empower all women and girls. So even for a sustainable world, this this goal is extremely important. I don't have to explain that, but I'm going to give you a flavor of it. For me, all it means is equal participation in decision making. And that's the most important thing. Whether you are deciding what you wish to do is your business, and decision making is really the key. So, having said that, let me just move to some things that we already know. Most of the obstacles that women face is to do with our socialization. There are many things you would hear. You would hear that women are not very competitive. I heard that a lot. We heard, we always have a bit of a complex, but that I think men also share. But our socialization in really make you believe that that's really is true, and there is something wrong with ourselves. There are many conscious and unconscious biases. I mean, it would take me 2 hours to just talk about anecdotes, and there's stereotypes. What I'm going to talk a bit about that. But then there's stated and unstated discrimination. That first line is a very heavy line. If you sit down and think, you'd probably have a lot of examples of each one of these. In India, officially stated policies have no gender bias, and I'm very proud of that. But that doesn't mean there are no gender biases. And that's really the problem. When you have something is wrong on your face, you can actually handle it. When you don't even know what is the problem, then the task becomes extremely difficult. So there are unfounded biases, for example. I don't know how many of you heard it. but I've heard this a lot, that physics is a male subject. When I was a student in Calcutta, I did not feel it. Our class had so many girls and so many boys. The day I landed in the US, I became a specimen, a woman doing physics PhD. And that had stayed with me. Some other time, maybe I'll tell you some stories. But these are totally unfounded. There is no logic that, neuroscientists would tell you. In physics and mathematics, I don't think boys and girls do it differently. There are other differences, but that are obvious. So what we had found in my time, that certain types of soft jobs are appropriate for women. You restrict them to school or college teaching or some secretarial work. And why do you want to do physics? That was the time when I was starting. And when I actually did a pretty good PhD and I came back, I found another kind of a problem, and I'm pointing it out so that you can rectify it. Because I did my PhD abroad, I did not have a godfather or a godmother in India. I got a job based on my CV. Nobody knew me really. I did not know anybody. So this network is needed as you take your first steps into the professional domain. So mentors are required. There's, of course, institutional sexism. If you look deep, you find it everywhere. Women have to work harder. Vandana was just narrating a story that you have to work harder than your male colleagues to convince your colleagues and superiors of your abilities. Similar kind of CV when I became finally the chair of selection committees. Similar CVs, one of a boy, one of a girl. I'll find my colleagues with all good intention, calling the boy a genius, and the girl extremely hardworking. Oh, very good CV. She's very, very hardworking. So this seems to be very common. So if I point it out, how do you know that that guy is a genius and this girl is just hardworking? And she worked with somebody extremely famous and did it. I said, so did he. He also worked in a group that was really, really good. So people with good intentions do not even realize that these are biases that are sitting in their head. The girl must be hardworking and the boy must be genius. Okay, so these are things that we have to do, but sometimes it works out, and that's our generation. We are very few, so we are noticed more easily. Sometimes it goes in your favor, sometimes goes against you, because you're noticed very easily. You do anything, everybody is going blah, 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 because you're a moment. Sometimes I find I'm a specimen really from the zoo. So, everybody is just, anything you do, it becomes like a thing to talk about. So these are things that more or less, more we talk about it, the better it gets. In general, there are many obstacles. We can look at them as challenges. And the moment you understand that, you see the opportunities of doing something. That's what we're trying to do even today. There are many, many problems with women, poor working conditions, toilets. You can't go on a long journey because of lack of problems, security aspects. You can't work. I'm an experimentalist also. You can't work alone late night in the lab. A colleague of mine had once told me that my daughter really is very impressed by you, but you work through the night and it's not safe here. So these are the kind of things that one needs to. Some systematic problem. You can't handle it alone, but you have to raise the issues again and again. Then after a certain age, you need childcare facilities. Creches are important, and proper childcare facilities so that both parents, not just the mother, actually both father and mother, if they wish to, they can actually concentrate on their work. And then the rest, maternity leave can lead to career break, lack of mobility because of family responsibilities. So sometimes you lose out on promotion somewhere else. So my own experiences gave me the advantage of understanding and prioritizing when I finally got a chance. And this is something that probably we should talk about at some other time, that I call creative leadership. What this means, and each one of you actually will become one of those, because creative leaders are the ones who think on their feet. And in a situation where the path is not known, the purpose for the team is lost, you still figure it out, what is the way forward. So that's something that probably has been an advantage. So I want to just make two more points before moving on to the hardcore physics, that why should the society bother? A dear friend of mine, a good mathematician, when I was the dean in JNU, we had organized a gender mathematics symposium, and Amber Habib came up to me and said that why should men give up the advantage the perceived advantage they have. What is the reason? So I thought about it because I never thought of it that way. And I came up with this, that it's really a gender-rich society is both desirable and beneficial. It's not just something morally correct to do, and I'm going to show that. But before that, just an English problem, equality, equality, equality. If you know mathematics, two human beings are never equal, they're not identical. So it's really a question of equity that we are asking for. And if we develop enough, it would get to a proper framework of justice. So reality is what you see. Equality would mean that everybody getting the same advantages. Equity would mean you get depending on who you are. And one thing that you must remember when you are getting into physics research, the higher education sector, so universities and research institutions, the strength is really the fact that human beings are not identical. Because we think differently, we fight, and because of conflict of ideas, new ideas come out. If everybody thought the same way, everybody was just the same, identical, then that would be the end of research probably, because nobody would be thinking of anything new. So we are all different, and that's our strength. And so scientific progress is only possible and greatly accelerated if you have gender equity. It's not just about treating everyone equally, it's about understanding the differences rationally. And I want you to understand that. The fact that we are all different, that's the strength. And that has to be understood rationally. And you have to ensure equity, making the best of everyone's abilities and choices. So these are important points, a lot of stuff in these slides. So the fact that I said it's also not just, it makes business sense, not just a morally correct thing to do, to talk about gender equity, because what you don't want when you are selecting some people, you want to engage the very best people, not just the best men and the next best men and the next best men, right? So if you want to stay competitive in business, you want to choose your best people. We cannot be competitive in a global economy if half of our human capital is not allowed the opportunity to work up to its potential. Okay, so that's one part of the logic. And the second is an important finding. In 2016 November, there's a Harvard Business Review paper. The title was something like this, I think B something, diverse teams are smarter. So it really, the cases were on businesses, not universities, but you could almost translate that to educational institutions to say diverse teams are smarter. So if that is the case, then diversity and inclusivity are not just morally correct principles for an institution, but it makes perfect business sense to promote them. And I want people to understand this very, very clearly. And our goal today, I would say, I've been saying this for the last 15 years, that we need to prevent a division of men and women into two opposing interest groups. So I written it like a binary, but So because then it's a net zero or net negative sum often. So it should not be that only women raise and fight for what people call women's issues. I hate it actually. So all right-thinking humans should be in this together. Okay. So I want you to understand this, propagate this, and then we'll have programs not just with women, but women and men together. So I'm a product of a generation where some of us have made it, okay, in spite of the system and not because of the system. And more, I wanted to change this for my next generation. That's how I got into administration. And whatever we are doing, we have to strive for excellence. And that is to stay competitive. And that's gender parity. One part of it, a big part, the theme is excellence. Right? If you want to bring in excellence, you actually need to have a fair system. And not just fair, I don't want to call it a gender balanced system. I want to call it a gender rich system. The second time I'm using this phrase, I coined it up, and I really think that that's what it should be. All of us are kind of different. So with that statement, strive for excellence in whatever you do. That's something probably you can see even from Bimla Buti's life and works and what she believed in. I move on to a little bit of physics that would be in tune with what Vandana just announced. Before I get into it, I just wanted to tell you that I hope you understand that the scientific methodology, as we call it, is really the gold standard that separates science from pseudoscience and the rest. So, this diagram I have copied from somewhere, I've forgotten, so I couldn't put the source. But essentially, what what is important is that to know that science has a framework. Only verifiable or falsifiable assertions are part of the framework. Okay, so if something that cannot be even proven wrong is not part of the science. In science, we do not talk about that I am in search of truth. The truth yesterday is not truth today. So nobody talks about truth anymore. So it's really a pursuit through a methodology that I have described in there that's the framework we believe in. And we keep trying to falsify it, right? So very simple example of what I'm talking about is people actually thought the earth was at the center of the universe. Then later people understood that this is not true, that sun is at the center, all the planets are moving our way. Today we don't say anything is the center of anything, we know much better. So the truth has changed, but each of those assertions at that time is also part of the scientific methodology. Okay, so I think that's the gold standard. And this is an ongoing process because, as I just explained, speculation and conjecture also have a place in science. Often you can have a conjecture in your paper, and I speculate when I see the data in my lab. So I think I shared this earlier, that when astrology was being pushed into the syllabus a few years back in Delhi government, I was sent by my Vice-Chancellor at the time, JNU, to a meeting where I was told that why are you objecting to it? Astrology has 50% success rate. So does medical science. So medical science, I call science. Astrology, I have so much difficulty calling it a science. And I hope all of you, if you have not thought this through, think about it and come up with an answer staring at your face by what is written. So astrology is good fun. You want to do on Sunday, you read it. I have no objection to that. But don't confuse what is science, which is verifiable or falsifiable. But astrology is not even falsifiable, right? It's good fun, but not falsifiable. So I think this is something that one needs to keep in mind as to what science is. The most obvious things people are forgetting. Sometimes you need to go back and see the most obvious stuff. So as I have written here, that an acceptable scientific theory must be verified by relevant observations and experiments. Till that time, it stays a conjecture or a speculation. Now, I worked in optics, quantum optics to be precise, and in optics, I take a lot of pride in saying that, the big evolutions are almost like revolutions, so drastic evolutions that were prompted by optics and physics. I would have no time to talk about the first one, relativity, which normally you associate with high speed. If your speeds are of within certain limits, you don't need to get into the relativistic domain. And similarly, people talk about quantum mechanics, which moves away from the classical mechanics in terms of small size. Okay, now these are not very proper definitions because I don't know what is high and what is small. I have not defined in the slide, but that sort of is the thing. The second one is what I'm going to talk about. So examples of this evolution in physics is something that I'm sure all of you know. In your first year MSc also you have read enough of quantum mechanics. It's around 1900. The electron theory of matter came up through experiments. People understood that inside the atom, if you just keep on hammering matter down and you get to the atomic level, then inside the atom there is a nucleus which is positively charged, which is very tiny. There's a lot of empty spaces in there. The negatively charged electrons are orbiting. Those names did not come in 1900 later, but anyway, the idea is that it then created a problem. What is the problem? The people said first, oh, this looks exactly like the solar system. So you have the sun at the center, planets orbiting around it. And here, actually, it's the nucleus at the center. The electrons are orbiting around it. It's the same inverse square law of attraction. The force in that case is gravitational, 1 by r squared. In this case is electromagnetic, so it's again 1 by r squared. The problem is electrons are charged. So when they're orbiting, Even if you assume it to be circular, you know very well this has an acceleration. And accelerate because there is a change of direction. Even if uniform speed, there is a change of direction, so there is acceleration. Accelerated charges emit radiation. Therefore, they would not be able to keep their stable orbits and they would collapse into the nucleus. Okay, so there is a grand failure of classical laws with this model. So a lot of people, see, the year is important, from 1900 to about 1924, 24 years people struggled with this. A board came, I mean, this is not the history that I want to talk about today, but something great happened by the time 1925 came, and it sort of, the evolution continued beyond 1925 as well. But in 1925, we say that this is really when modern quantum mechanics was born. Heisenberg developed the matrix mechanics, Schrödinger invented the wave mechanics. Subsequently, it was shown that both are identical. So that's the year 1925. And the title that I've given, and as Vandana pointed out, this is really a century of development of quantum mechanics. So next year will be the 100th anniversary of development of quantum mechanics, and UN most probably tonight, our time tonight, will declare next year as the International Year of Quantum Science and Technology. So there will be a year-long initiative. We'll talk about it. So essentially, what I'm going to do is give you a flavor of the research that has happened in these 99 years. That's a tall order in half an hour, but I'll touch upon the most important aspects where the bottlenecks have been. Okay, so another thing happened. There's a lot of excitement even in the bureaucracy and everywhere, because last year, 1 year has already passed, the Union Cabinet announced a huge budget of 6,000 crore for this national quantum mission, which is supposed to run from 23 to 31. 1 year is already gone of the 8 years, so 7 years left. And the 4 thematic hubs are going to be set up, one on quantum computing, quantum communication, quantum sensing and metrology, and quantum materials and devices. So almost all the academicians in the country have got involved in this, in trying to actually propose things. What would come out of it, I don't know. But anyway, right now, I sense from very close quarters a lot of excitement. Another great thing happened before that. This is a long due recognition that Alain Aspect, John Clauser, and Anton Zaileria got through the Nobel Prize in Physics in 2022. The citation in the Nobel Prize says for experiments with entangled photons, establishing the violation of well-known inequalities, which I'm not going to talk about today, and pioneering quantum information science. So this really has happened over a long time, and I have been involved in the initial development of this revolution. So I'm going to actually show you some historical papers of that time. So people also refer to some quantum revolutions. I don't like it much, but just in case you read some things and you find the first, this is not the 1925 wala, this is after that. The first quantum revolution enabled lasers and transistors based on the rules of quantum mechanics or devices. And the second quantum revolution, again a bad name, that aims to control quantum systems. That's where we are in right now. And so quantum technologies today seek to use quantum phenomena in all of these that I talked about to go beyond what classical systems can do. So what really is the crux of the matter? So to say that, I'm going to talk about a few counterintuitive quantum features, and going by something extremely simple. It's basic Feynman lecture, volume 3, first chapter. Okay, it's as simple as that. It's important to go through it once. Okay, you imagine, because my field is also optics, so I'm just going to do this with you. So imagine a first experiment where I have a photocathode where I'm shining light on. Every time light is falling on this photocathode, photoelectrons are getting ejected. So you take those electrons, that means a tiny nanoampere current is actually getting formed. You amplify that and you feed it into your speaker. So every time light strikes on the photocathode, you hear a click in the speaker. So that's the first experiment. If you do that, the experiment you have to do is get a variable source of light. So you started with 1000 watts, make it 500 watts, 100 watts, 50 watts, 10 watts. And as the light gets dimmer, you hear the clicks. What you hear is the clicks remain as loud. So they're click, 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 click. So they're equally click, 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 but there are fewer of them. Click, 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 each equally loud. So the conclusion you would draw is light is something like raindrops that much later were called photons or bullets, if you like. If the light is all of one color, same frequency, then all the raindrops are the same size, same energy. You do a second experiment. Also, don't have to do it, you see it all the time. This involves partial reflection in just an ordinary glass plate, which is 4% reflecting. You shine light and you make it a very dim source. So what people say is, if it is naturally 4% reflecting, 4% of the photons that are falling on it get reflected, 96% go through. So when the question is, how does individual photons know which way they have to go? So if one photon strikes the surface, it has two possible paths: get reflected, get transmitted. Each one seems to be having a mind to know, oh, 4 of them have gone there, reflected, so I better go transmitted. Physics is becoming really ridiculous at this level, single particle level, that the difficulty is how does a single photon know which of the two possible paths it should take when it hits the glass surface? How does it make up its mind? But you do this experiment n number of times on an average, that's important. You'll find 4% gets reflected, 96% get transmitted. So if you want to find out what is the trajectory of each of those particles, you get confused. And it's a deep mystery. Till today, we don't know the answer. So there was a time where Newton's or their particle theory was not satisfactory. Partial reflection of the kind of second experiment could be explained by a theory of waves, but the wave theory could not explain the clicks of the photomultiplier theory in the first experiment that I just described. So there was a period in which one had to know which experiment one was analyzing in order to tell if light was waves or particle. This state of confusion was called the wave-particle duality of light. So this is what your teachers tell you not to do. You're predicting, depending on the experiment you are doing in the lab, you are actually going back to one theory or the other. It's back calculation. Nothing worse, nothing better. So this is also a joke from Feynman, another book, I think. Light was waves on Mondays, Wednesdays, and Fridays. It was particles on Tuesdays, Thursdays, and Saturdays. On Sundays, we think about it. So this was as ridiculous as it was. And this sort of explains to you, because optics is so visual that you can actually see where the problem is. So that led to the field of quantum optics, where I work, that it reconciled the particle properties of light with the wave nature. So it's one theory that combined everything. And it's the quantum version, the second quantum, we'll call it, of the same quantum mechanics. So it sort of says that asking the question whether light is wave or particle is the stupid question. What is a stupid question? The stupid question is the one for which you cannot give an answer by an experiment. These experiments cannot decipher. Otherwise, you can ask any question one can attempt. But it's a stupid question to ask when you know no experiment can actually decipher that. Okay. So familiar to unfamiliar interference. So let's just go back to something extremely familiar to all of you. I've already given a sense of this in the sense of the partial reflection, where people call by all kinds of name, division or amplitude, division of wavefront, whichever. So this one is the other version of it. So in this case, you just have a source at S, and there is a screen in which I have made two tiny holes A and B, and there is a detector D which I am sliding up and down. So for no loss of generality, let's assume that the source is emitting photons of one color, and one photon, it's a very weak one, so one photon at a time from the source to detector. If you close one of the holes, say I close B, then say the detector clicks 1% of the time. If I do the opposite, I close A and open B, then I get, say, there is perfect symmetry, I get 1% clicks at the detector. When I open both A and B, I get something very funny that we call interference. Opening a second hole does not always increase the amount of light reaching the detector. It depends on the position of the detector. At some points, you get light plus light, no light at all, right? So it tells you when I'm doing light plus light and I'm getting a 0, that means both, if they both are equal, then one is the opposite of the other. It's not the intensity, the positive definite quantity we see, or power or whatever you call it. But it's something that the physics of superposition is happening at a level below our seeing abilities. Okay, and that's really a simple idea, but it's something very, very counterintuitive. If you do this experiment, what do you see? Okay, I'm on Feynman. So if you look at the volume 3 first chapter, he says that if you choose to examine a phenomenon which is impossible to explain in any classical way, which has in it the heart of quantum mechanics, it contains the only mystery. And it's so true. And today, perfectly agreeing with this statement. And I urge you to look back at this and understand. So if I shoot really one photon and I keep looking at the detector, you'd find, and there are beautiful movies with electrons that are available on YouTube, that you get only one tiny dot appearing on the screen, kind of looks like random. But if you throw a million electrons or million photons, the pattern starts emerging, dark and bright in different fringes. So Dirac had said that we should think of the single photon as being associated with both paths simultaneously. So there's no clear concept of a trajectory, like I throw a ball, I know it will form this parabola and it would fall down. And you can't have this uncertainty when you're shooting a rocket to space, right? You can't say that either it's this way or that way. So classical mechanics has this determinism, which is getting violated at a single particle level in quantum mechanics. This is what we call quantum mechanics. So there are two consequences of this that you would hear a lot, that quantum mechanics doesn't have any reality. So earlier we thought physics is just trying to measure, there is an objective reality out there. I'm just trying to actually get some elements of that reality by observation. It says it's actually not that, depending on who is observing and how the reality is changing. So there is no reality which is independent of observers or measurement. So, Einstein's concept again, if I ask you, does the moon exist? And you would say yes, because either you have seen it or somebody who has seen it has told you. Right? So I think in this concept, it doesn't really exist till you observe it. And there is no locality. There is an extent of the wave function. For example, right now I'm in Bombay, nobody is seeing me in Delhi. Had I been a quantum particle with an extended wave function, I have a finite probability of being detected there as well as detected here. So the question that you would ask, so what if many photons or atoms are linked in a single wave of light and matter? The funny things will actually happen. And then you would ask the question, how do you go from our familiar classical world to that quantum world? Is there a door? Or how do you come from this counterintuitive quantum world to our familiar classical world? Is there a door? Is there a crossover? So this is something that we have to use. And then second important thing everybody would ask, what's the use of all this nonsense? Because how does it matter? So quantum mechanics demanded a whole change in philosophy. From the determinism of classical physics, you got into quantum mechanical predictability, which can at best be probabilistic. So there is an intrinsic indeterminacy. It has nothing to do with how good or bad you are as an experimentalist. It's in principle doable, in principle not doable. Okay? And that's really the question that led to many conceptual problems. Of course, Einstein dismissed this uncertainty by saying God doesn't play dice with the universe. And I don't know what he meant by God, but I've written something there. This is something we always struggle. There are things from even Hawking's, right? He had clearly stated there is no God. I don't think there is any God who created. There are laws of science you believe in. But anyway, I think Einstein believed in mathematical laws of nature. His idea of a God here is perhaps someone who formulated the laws and then left the universe alone to evolve according to these laws. I don't know. So all of this to ask the question, what is the use? It emerges that I have actually chanced upon a very, very powerful resource. And that's called a quantum entanglement. What does it mean? This is what Einstein called spooky action at a distance. If two particles had interacted or they're sort of born like a twin, so even when they move far apart, you do something to one, the other one gets affected, as if this one is transmitting information instantaneously to the counterpart. So that's the spooky action at a distance. So what happens to one of the particles in such a twin pair determines what happens to the other particle. So this is something that we chanced upon, and I'm going to really talk about this quite a bit. If you remember, that was one of the things that you got a Nobel Prize on. So Dirac's classic book in 1958 has the statement that each photon in this interferes only with itself. Interference between two different photons never occurs. Okay. Now, this is something that my thesis I violated, and I showed that possible to make two photons being emitted by independent sources interfere. So we'll sort of have to take a look at it. This part I'll go very rapidly and not really give you a lot of details, but essentially it's something that we call light in quantum states to be used, and then you can actually violate that. This is the old papers. One is the theory first, and then the very well quoted experiment, and it has appeared in textbooks, etc., etc. You can't quite read it, so I'll just read out one particular aspect of it. This book talks about a new source from nonlinear optics. Alan Espes, as the Nobel laureate you saw, he perfected this source, my note there is the calcium cascade, and he went on to use it in an important series of experiments that examined the physics of entangled states. But around 1985 at the University of Rochester, that's me actually, through a process known by the intimidating name spontaneous parametric Down conversion, a single UV photon can fission into two infrared ones if it is passed through certain crystals. So this is something that we did a whole range of new experiments with. So this is a new source and it's a new experiment. So we sort of did an experiment similar to the Einstein-Podolsky-Rosen thought experiment in that the two observers might actually compare their data in order to realize that anything interesting is going on. So it's a two-photon correlation experiments, and I'm going to talk about this a bit in a simpler way. Before that, this has also appeared in a different context in popular science books, very worth reading, The Age of Entanglement, where it's saying it sort of dramatizes what I was doing. And I have corrected this, but I showed this in the other conference, where you see it says turn from theory to fact by Rupamanjari Ghosh working on his PhD was in the book. I corrected it, and it shouldn't have been, it must be the other slide, but anyway. I wrote the lady had actually talked to me on the phone. I was Jane for clarification, and she knew it was a woman. And still in the book, it appeared as his. This is the bias. And then the corrections have, of course, come out and it says her PhD. But anyway, that's just a story. So my work is kind of sandwiched between aspects and Zeilinger, the other Nobel laureate, where we did. So what my experiment, the silly looking figure on top is from my paper, where I'm shooting a UV palm photon and it's actually splitting. There's a spontaneous photon splitting happening into signal and idler, historically called two photons. So, in Maxwell equations, photons, there's a linear, photons don't talk to each other, they don't interact. But in a material, you can make them interact. Okay, so that's gets you into a nonlinear domain, and you can actually create these around the signal and the idler, the cones of color like this that is shown. But this photo is not from me at the time. The intensity was too light. This photo was from Zeilinger. So we've kind of worked on this much later, many concepts of this, but it's to do with this correlation that you find in a quantum process. When you are born together, you sort of keep on affecting each other that way till something destroys that coherence. I'm going to talk to that. So what is the concept? The concept is, if this really is true, then maybe this quantum parallelism that you're going through slit A and slit B, and not all, and slit B simultaneously. An atom can be in an electronic state upstairs and downstairs simultaneously. If I could be a quantum particle, could be in Delhi and Bombay simultaneously. This parallelism, if you could exploit, then probably you can create a hugely powerful computer which works on this principles of quantum mechanics. So instead of a bit, which is a binary digit, which is just strings of zeros and ones, you now use what we call a qubit, a quantum bit, which is a mixture of these zeros and ones, no and yes together, kind of like maybe, which has infinite possibility of carrying information, something that's both dead and alive together in our macro world. And because that carries much more information than just being dead or alive. So the real question then becomes how to produce, observe, and make use of such powerful information-rich states. Why this is a question? Because the question I'm asking that I don't see such strange things in my day-to-day world. I don't see a cat which is both dead and alive. I don't see myself both in Delhi and Bombay. So what exactly is happening in this, and how do we actually describe dynamically the transition from or to classical to and from the quantum world? So that's really what in that book also is called the quantum challenge, that quantum mechanics shows up in small enclaves within the classical macro world. The behavior of the individual constituents, for example, atoms and photons, are described by quantum mechanics, but these are rarely isolated from their environment. And as they interact with their environment, they lose their peculiar quantum character. They become classical normal. Okay, so a central question in quantum physics is the mechanism of transition between the quantum and the classical world. So to make a measurement, one not only needs to keep a quantum system isolated for long enough, right, so that it retains that quantum coherence of mixing up Delhi and Bombay, but also probe it delicately. Remember that reality gets disturbed by when you're observing it. If you're putting a detector to see whether the photon went through A, that wonderful interference pattern disappears. It just then goes to either A or B, not A and B. So this single particle detection problem was known. The problem was known to even Schrödinger at that time, around 1952. He called it post-mortem physics because when you are doing the post-mortem, you're actually dissecting, so the body is destroyed. So this destroys the object under investigation. So now the Nobel Prize and previous ones as well, 2012, 2005 as well, 1997 cold atoms, is observation of such fragile quantum effects are becoming a possibility. And this is something that you already know, the so-called Schrödinger cat paradox. I would not spend much time on that. So till if I assume the cat and the radioactive nucleus as quantum particles, then the radioactive nucleus fires, then the poison gets emitted and the cat dies. If it doesn't fire, the poison is intact and the cat is alive. Till you open the box to observe or do a measurement, the cat is in a state of both dead and alive. And that's really is the quantum mechanical thing. So bringing up to date to this, there is a popular level article in March 22 by Shankar Das Sharma, the name may be familiar, that he says the main issue with quantum computing is that quantum states decohere in the presence of environmental noise. Okay, and so the article says quantum computing has a height problem. But to do effective quantum computation, you need to have entanglement of large quantum states so that you can do efficient calculations. Such states will necessarily interact with its environment. And the moment it interacts and it's not isolated, so these are extremely critical inputs in the scheme of quantum information processing. So this is something we need to understand, the process of loss of coherence and emergence of classicality, and quantum error correction is the single most important technology for the future of quantum computing. Now, when we are doing a lot of work on decoherence, we also realize that it's not just for quantum computing, quantum information, because you understand the problem. The time to perform elementary unitary transformations involving qubits should be well within the quantum coherence time. Beyond that, it doesn't stay quantum, it becomes classical. But it also has a thing with quantum measurement problem that I talked about, an explanation of emergence of classical world from quantum mechanics, and arrows of time problem, which is something very different, and I'll not get into the details of it. And why does time never go backward? right? In space, we go forward and backward. In time, we just go from birth to death. Okay, and you never, it's irreversible. But in special theory of relativity, remember space and time were treated equivalently. So you need to understand errors of time problem, and one answer, I'm not saying it's the only answer, comes from this theory of decoherence. My group actually had done extensive work on the dynamics of open quantum systems, understanding this loss of coherence business dynamically, believing in quantum dynamics. So what are the typical questions? By then, if you're not, if you are feeling sleepy, you have to ask these questions. They're not answered yet. How does decoherence evolve in time? How does decoherence affect n qubit entanglement? How does it depend on that n number of qubits? How can decoherence be controlled and or tested experimentally? So only when you understand something, you can control it, right? And I think that's really the idea, that you need to do much more studies on decoherence to understand it. And the last few minutes, I'll give you an example of quantum memory. That's something that we worked on. It's an interesting phenomenon, has a lot of side effects. So this phenomenon is called electromagnetically induced transparency, EIT in short. And as the name suggests, it's about transparent, making otherwise opaque medium transparent. It's an induced transparency. So naturally, as it is standing, it's an opaque medium because light falling on it is getting absorbed. Okay, this is on resonance. So you can well imagine some population is getting lifted upstairs maybe, and so no light is coming out. So by using a second control laser, I can probably make that material transparent, even on resonance. And that's the idea of EIT. The picture is just a cartoon. You're familiar with this delta is the little detuning between the energy level spread between these two omega naught and the laser I'm probing with omega. Okay, and if I just plot absorption, it would have a peak exactly at delta equal to 0. So when the laser is on resonance, it's lifting the population up. Don't imagine it exactly, it's just a cartoon. It's just spending the energy lifting the population up. And so maximum absorption is happening when delta is 0. And correspondingly, you have a dispersion curve, which is a sharp negative dispersion. This is standard Jackson or whichever Griffiths, whichever book you are following. I can add a second level, a third level, and a second laser, which would be the control one that changes the curve drastically like this. Okay, where you had a peak of absorption, now you have a dip. That means it's a transmission window. So there is a small transparency window in which the dispersion curve really changes drastically. It now is a very sharp, steep dispersion curve, but it's a positive slope. And so if you look at it carefully, what happens is that this extreme positive dispersion gives rise to a phenomenon that we call slow light. Slow light should not be so surprising for you. Light propagates in free space with the highest number that 3 into 10 to the 8 meters per second. Through any material, it travels slower. Refractive indices you are familiar with, water, glass, air. So you know of 1.5, 1.33, semiconductors need a 6, okay, or so and so. But now I'm talking about a group index, which is 10 to the 6, 10 to the 7. So light goes at the speed of a cycle, bicycle, inside the material, so slow. And so how slow can it get? If I'm actually getting slow light of this kind, by using this positive slope within the transparency window, you can see the formula I've written there. Vg is the group velocity, which is c, the free space speed, divided by this slope, essentially. And so this ng, the group index, can be really, really large because this dispersion is positive and really, really steep. How slow can it get? Can you actually stop light? Right? So that's the question. The answer is not really. But in EIT, again, before I forget, it's all about interference in quantum mechanics. If I did not have to play with the phase of the field, for example, I don't need to have quantum mechanics. I could have just done with classical systems, everything that I could have described. So the phenomenon of interference confronts us with two fundamental quantum ideas. One, probabilistic interpretation. Second, addition of probability amplitudes for indistinguishable paths. Really horrible, but that's just a calculational tool, right? Following direct. Physics of EIT also you can describe accordingly. There are multiple routes to excitation. One is a straight one from B to A, direct. The second one is a nonlinear one mediated by the control laser, which is B to A to C to A. Okay, these two paths, these two excitation routes interfere. These two, indistinguishable paths, because the control laser is really, really strong. Strong actually is milliwatts. That's good enough for these systems. It leads to cancellation of absorption along B to A. So nothing goes up anymore because these two paths are interfering. But it also has a coherence time like you had in double slit, right? This coherence time is called Raman coherence time very significantly. This is all about this two photon path. So everything, if I do within that Raman coherence time, I'll actually see this quantum effect. But this quantum effect is also not from a small system, it's bulk quantum mechanics at room temperature. And that's what we actually did. So the general EIT scheme, you always have this lambda, capital lambda system, where you have this weak probe, which is the laser that is actually probing, and a second laser called the strong coupling. Details are not really important, but the point here is the dark state, that's the lower ground state that we have prepared. It's called a dark state. This transition is really on resonance, right? Because the probe laser is exactly on resonance with the arm B2A. But the poor fellow is actually not seeing the light because interference is cancelling that relevant dipole in that. So it is really the dark state in spite of being in light. Okay, so this is a quantum interference effect of a different kind. So the idea is that you can control the behavior of atomic medium to switch between transparency and absorption and do whatever. So the trick is really to select a simple usable atomic level configuration. Real life atoms are not so simple as a lambda system. So that's what we did. And then some experiments were conducted in bulk room temperature helium-4. And this was actually done in through my collaboration with this French group. Fabien Brevnecker is a longtime friend with several institutions we have done. And Fabien Goldfarb was really setting up the room temperature helium-4 setup. We have done multiple projects, each one got excellent graded, and this is just something that you should actually repeat up. The second one, when I did, I was the Vice-Chancellor of Shiv University. It was not easy at all to take out time because I was just building a new university, and an article came out. A lot of work on that we have done from our group. But I want to actually point out something very crazy here. If you look at the simple formula I have written down, the group velocity through the material is C by Ng. So I'm now talking about slow light when Ng is much larger than 1. Right? So group velocity is much smaller than C. I can also create a situation where Ng is less than 1. So I'll have fast light because Vg would be greater than C. Does that trigger an alarm bell? Because yes, because you have been told in textbooks that group velocity cannot exceed C. When I was a child, in our textbooks, it even said no velocity, phase velocity could exceed C because you would then violate causality. That was a secret thing believed by people. Einstein gave it to us from special theory. There is no proof of causality, but it's something that's a secret principle in physics. If it is not there, what would happen? Cause and effect relationship would go crazy, right? So the effect would appear before the cause. So you could kill your grandfather. If you could move faster than the speed of light in free space, you can go to your past, kill your grandfather, so you will not be born. So see, the world would become a total mess because nothing would make any sense. There will be no causal relationship with anything. So fast light was actually prevented. In whatever I'm showing, there's no such violation. We have to just rewrite textbooks because it doesn't say that information travels with this group velocity. By the time I was in the US, people have already done Charles group experiments to show that phase velocity, that's the speed of one frequency component in a light of multiple colors. That could be larger than c. Now I'm saying even Vg could be larger than c. Then group velocity doesn't carry information. You cannot carry information faster than c. That's the statement of causality today. It's much more complicated than what I'm saying. If you think about what does it mean in the quantum domain, there's no concept of speed there of the kind that we're talking about. It's not really fully solved. So can take it up and you'd really solve a mystery in physics. Okay, having done the one lambda, we have gone ahead. I'm not going to talk about this at all, but the idea is that you really then cook up schemes, and this is a double lambda or like a tripod. It's a 4 levels, 1 extra, 2 lasers. So 4-level atomic system, 3 classical fields, 3 Raman coordinates, 2 dark states. It gets very, very complicated if you are good at computing, which I, a PhD student of mine did that. And this kind of systems have a lot of application as a switch, and the control variables are laser light and magnetic field both. Okay, so that's something. So what is the summary of what I have just said? That you could actually start and restart light at will. This is contrary to, again, a fundamental physics, and I thought it would be appropriate to tell you this. Photons have 0 rest mass, and therefore they cannot be at rest. You cannot have V equal to 0. But when I make the light beam interact with matter, photons acquire a mass. These get dressed up. Okay, condensed matter physicists look at it from the matter side. We people look at it from the optics side. We actually do the same interaction. So this light plus matter interaction creates rest photons and rest atoms. So their concept, for example, very familiar in condensed matter, polaritrons. Those are joint oscillations of light and collective atomic dipoles. So these polaritrons have non-zero rest mass. Therefore, you can have 0 velocity in a moving frame of reference. So a lot of new things you can actually do when you have these interactions permitted, and they are not isolated systems, but light and matter are interacting together. So there are other kind of mechanisms. You don't have to look at all of it, that there is self-stopping of light, all kinds of things people are coming up with. But incoming light can carry information. It comes to this material medium where I use it, say in the EIT configuration, I turn on the control light. Nice thing in optics is the moment I turn off the light, it's back to normal. So the light carries information, comes in here, I turn on the control laser, EIT takes over, and all the information I had in my light beam is stored as spin oscillations in the material, and it stays there all within the coherence time. Okay, and then when I want the information out, I turn on the control laser, out comes the original pulse. So the real question is, that's what is written in here. I had a video which I created, but I didn't bring it this time. So the point is that quantum memory is like getting from flying qubit to stationary qubit and vice versa. But the real question is, it has to be at will. The photons can't decide when it wants to come out, and so there you have a control. And the entire question is about this, that the quantum information I'm coding, I don't know what it is. The moment I know, meaning when I do a measurement, it doesn't stay quantum. So here is it, you are storing a piece of information which you don't know anything about, and you need to retrieve it with 100% fidelity. So you have to devise a process in which it happens without your intervening in between, without your looking in between to say, oh, this is the actual quantum state, so I know I have got it. The moment you did it, quantum state disappears, right? It becomes a classical one of the two possibilities in a statistical game. So there's a lot of information that's there already in some review I have quoted here, which you can take a look at it, and a lot of work happening. in this to store and release single photon and maybe complicated versions of it in which you are storing more complicated information. So how big is this coherence time? How soon do you need to finish your operations? And this is one paper that I'm showing from Weizmann Institute of Science that 1 second is a fairly long time at the research level. Mine was micro. That was also considered to be very large. But in 1 second, you can actually do easily 10 to the power 9 operations without having to do much. So they were shown in room temperature cesium cells. Again, a room temperature system like ours was. And there is a lot of work going on in this. So today I don't want to go on and on. There is a lot more detail that we can talk about this. If you focus on what is the state of the art, I hope you understood what the basic thing. Everybody is familiar with WWW, the World Wide Web. In the quantum version of it, the quantum internet will process and store quantum information through these qubits that I talked about. And that has to happen in a quantum network. So for data transmission, this is kind of the system that we have in mind, that the channels will be photonic, because photons cannot be localized very easily, but they are neutral, so they normally do not decoher very fast, and they are very high speed, so they can go from one point to another with very high speed. So your channels will be photonic, but your nodes or memory would be atomic, right? So they are good quantum memories, but difficult to transport over distance. So you need to basically create an atom-photon network. So the photons carrying the quantum information in qubits in which you were formed, transferring to the atomic system, the atom storing it as long as you need, and then it's sort of going further. So that's a basic, very simple-minded network that you can think of. The real question then stays about the information transfer problem I mentioned, right? So how do you transfer the information that you don't know anything about? Because knowing will kill it, right? So it stays quantum, and you transfer from the photonic system to the atom back to the photon, again with 100% or close to 100% fidelity. So I end with this, that, probably you would ask me, I talked about the first quantum revolution, the second quantum revolution in the 99 years of quantum mechanics. What's the next quantum revolution people are waiting for? And I didn't show you examples because of lack of time today, but I would guess that commercial innovations in cybersecurity, energy, and beyond would be the next revolution one is looking at. Now, earlier commercial things were outside academics. We didn't look at it. None of us were any good in thinking about it. So here we are not talking about just tweaking some specs and coming up with a startup. Here we are talking about commercially making these kind of systems available. So I'm making a distinction between innovation and invention. Not tweaking of specs just for an innovation and for making money, but invention of the kind the world is looking and waiting for. Both in cybersecurity, because it's coming, energy definitely, and much beyond. So I expect youngsters to take the lead. If it is something that you are interested in, the world is going crazy over this, and these kind of commercial innovations we'll look at. That's my last slide. I did not plan it initially, but just to give you a flavor of stuff, let's end with something a little silly, but not so silly. Next to me, on my right, probably you know the face, Ashok Sen. Yes, he was at HRI at that time, now retired, but when Yuri Milner, this fundamental physics prize was announced, there are 9 winners in the first batch. Ashok Sen was one. They got $3 million. At that time, the value was something like 16.7 crore in Indian rupees. That's the most lucrative academic prize in the world, because if you look at the Nobel Prize, it's 1.2 million distributed amongst 2 or 3 people. So something as abstract or unremarkable as unmarketable as fundamental physics can indeed be very profitable. So you, of course, you win twice, right? I mean, you win all your life because you're doing something that's your passion. and you're benefiting from it. So your passion, your hobby is actually something that's supporting you by giving you a salary. And then Milner, do you know his history? He is a physics dropout. I don't want to talk too much about it, but it's an interesting story. Then he made these millions by some other method, which you can find out. Then he realizes how important it is to do fundamental physics, that he institutes this prize. So something to think about. In the world out there, the market is recognizing this to be something important. So maybe we are not doing it the wrong way. But I think the other incentives are, of course, there. So moral of the story today, what I tried to share with you is that physics evolves when theory and experiment go hand in hand. Okay? And from that evolution, profitable applications do come out. And one such application that today everybody is excited about is applications of quantum mechanics. Even in security systems, for example, when you go to the ATM and you withdraw money, your banking system, mostly the security of it is dependent on our inability to factorize very large numbers. But the problem with these kind of security systems is that what was a tough problem yesterday becomes an easy problem today. So if your entire security is based on your inability to crack a tough problem, what was a tough problem yesterday would be crackable today. But instead, if your security is based on natural laws like that of quantum mechanics, you can't break it because that's a natural law. So that's where the transition is taking place, and that's kind of applications that you will see. And it's the triumph of the scientific methodology I talked about: rational, observable, and provable and falsifiable. And that will continue. So it's not like one day Vandana and I will wake up that everybody has solved all the problems and we are jobless. You're just going to push the knowledge frontier further and further. Each push is taken, more and more effort. So this methodology will continue. And I thank you very much for your attention and wish you all the best, those of you who are graduating from this Vigyan with Vidushi. Thank you. Questions?
Thank you very much for a wonderful lecture. It's very nicely you introduced initially the gender part, the gender rich using your phrase, scientific methodology, and covering such a wide breadth of all this quantum entanglement and relating it to the application. It was nice to see glimpses of your thesis work. Of course, we'll have time for a few questions. Ask questions.
My question is regarding phase velocity. I read somewhere that monochromatic wave doesn't carry information. So I wanted to ask in what sense we say that it doesn't carry information. For example, I can send a monochromatic light from here, and some other person can detect it and know that some source of like I'm present here.
So all this has to do with the process of coding. There is a carrier. On top of it is a horse and the rider, right? The rider is the information. The monochromatic light, if you just think of it, the way it's propagating, every time I actually want a rider on it, I turn on something. I'm giving you a very simplistic answer, You turn on something. So in all these wave profiles, in time, there is a disruption, sharp kind of a shape change, if you like. So if you take a Fourier transform of that, so you look at a very sharp in time profile. If you look at what is the corresponding frequency profile, right? What should it be? One frequency or many? In time, if it has this kind of a disruption, I've turned on a coding system. So it can't be monochromatic. So in all practical systems where you transmit information, You're always turning off, on and off, on and off, one and two, one and zeros, right? So that cannot actually have a monochromatic spectrum. I can give you a mathematical response, Kamita, but I think you got the feeling. It's the same problem that I'm talking about even here. So a very smooth curve anyway, even a VG, which has multiple frequency, but each one smooth, doesn't carry any information.
By talking about your thesis, you mentioned Dirac statement, in which he said that light can only interact, only interfere with itself. Of course, your work shows that it's possible to have two light sources with each other. Should you modify the Dirac statement so the light can interfere with itself? Because the single photon can interfere with itself, as opposed to
Yes.
can also only interfere.
Yes, it does, but I think Dirac's interpretation of quantum interference holds, because I'm also using it. I'm also saying there are two indistinguishable paths corresponding to these paths, the probability amplitudes interfere. So I'm taking his explanation of that kind, but the statement is not strictly correct. It's not correct.
Anyone else? Terms of doctor already, but I just have one small question. So how soon you think it's going to be this in the real life? Like you gave an example of ATM. So when we would have something based on the quantum systems?
Things are moving very, very fast, particularly outside India, very, very fast. Some systems are already available, but quantum computing is not there. So 10, 15 years, I would say, there is a lot of excitement about IBM and Google, mostly IBM, about the number of qubits. So they have crossed 1,000 qubits, but that's not the only issue. The decoherence is the main problem, but the more important is all of them together should follow the same quantum dynamics. So that part is the trickiest part. So a lot of work has happened already. I think the next 10 to 15 years, small applications we are already seeing.
See, are there any more questions?
About that superluminal motion, can you elaborate a little more on that? Because is there a possibility that it just appears to be superluminal?
No, superluminal in the sense that the group velocity is actually exceeding c. Okay, but I'm saying now group velocity in these situations is not the one that carries any information. So superluminal, yes, but not carrying information. One needs to understand very clearly then how information is carried for causality to be violated. So superluminal, but not violating Einstein's causality is my statement.
Thank you.
Anyone else? Not. Let's thank Professor Rupamanjari for being very inspirational and motivational talk. Thank you very much.
Thank you very much.
Have a cup of tea.